Hello everyone, my name is Alex Tomsic. I'm the Director of Engineering for Red Wolf Reliability. This is the next video in our series on the introduction to the Voyager FDS sensor. Specifically, we're going to talk about journal bearing operating theory a little bit more today. And if you haven't seen any of the previous videos, feel free to watch them on our website at voyagerdynamics.com just so you can catch up. We've gone through a lot of different topics about our FDS sensor, fluid film bearings, so please feel free to check that out. So specifically, we're going to discuss in this video the expected oil pressure distribution and a few different styles of fluid film bearings. And then we're going to use that expected pressure distribution in our oil film to discuss how we decide where FDS sensors should be installed on these different varieties of bearings. So over on the right hand side of the slide, you can see a GIF of a plain cylindrical journal bearing. If you remember, we used this as our example in the last video discussing fluid film bearing fundamentals. One important thing to note is a plain cylindrical journal bearing is just one example of a fixed geometry fluid film bearing. And one thing that all fixed geometry fluid film bearings have in common is what's called cross-coupling. So cross-coupling is the response where your supporting force from your oil wedge is actually accompanied by a shaft displacement not only against your load, in this case the weight of the shaft or the rotor, which is in the vertical direction, but also a perpendicular displacement in the direction of rotation. So that cross-coupling in a fixed geometry bearing is actually what leads to our attitude angle that we discussed in the last video. This is a characteristic that's very specific to a fixed geometry bearing, and some of the other bearing designs we'll talk about don't actually show that. The animation on the right-hand side of this slide shows our oil pressure distribution around the circumference of our plain cylindrical journal bearing during a startup event from about 100 RPM to 3600 RPM. Now, just keep in mind as you watch this animation, this isn't at a constant speed. Remember, at rest, our rotor would be sitting on the bottom surface of our journal bearing. After we start up, we develop a thicker and thicker oil wedge to support that rotor. But initially, right after startup, you'll notice in this animation that we have a very skinny area that supports our rotor. But our magnitude or our amount of pressure at that area is actually high. That's because we have a fixed amount of load that we're supporting due to the weight of the rotor. And so the smaller the area that's supporting it, the higher the oil pressure has to be to support that load. Now, as we increase speed, we develop an increasing oil film thickness, and we actually spread that area out that's supporting that load, or that shaft in this case, and our oil pressure actually decreases from that startup. Now, you'll notice if you watch closely, the area that supports that shaft increases further as we speed up, but the magnitude actually increases a little bit as we get close to that 3600 RPM. That's because we have a certain amount of unbalance on this rotor, and so unbalance changes with speed and increases with speed, so our load actually is changing a little bit throughout the whole simulation. Now, there's a few things that are important that we can kind of extract from this about fixed geometry bearings in general. First, in a horizontal configuration like was modeled here, where the weight of the rotor is pointing down, our highest oil pressure occurs at the bottom dead center location, right below the shaft. Now, if we wanted to understand how much strain was occurring in the housing, you would want to mount your FDS sensor at the bottom dead center location on the bearing housing below the shaft. It's important to kind of discuss the oil pressure, right, where you have high oil pressure. That's what transmits the load from the rotor to the bearing housing. And so we want to be in that location of highest oil pressure. And that oil pressure follows the load. Now, the other important thing we can draw from this is that the oil pressure decreases really rapidly in the direction of rotation from BDC. So if you follow that green arrow around counterclockwise, from BDC, we actually hit a point where our oil pressure decreases to about 0 near that 45 degrees from BDC. Right, and that's following our attitude angle counterclockwise from BDC. We actually would recommend putting an FDS sensor there as well. The purpose is you expect low oil pressure, so you should have low strain values at that location, and that tells you a lot about how the bearing is operating. If you have higher strain values in that location than BDC, the bearing's operating in a really weird condition, or there's other loads that are affecting that bearing. So the animation on this slide shows the same oil pressure distribution as the previous slide was showing. The difference being, the previous slide was showing a maximum oil pressure across the circumference of our bearing. Now we've unrolled that bearing and flattened it out, and we're looking at a 3D distribution of our oil pressure, and this shows an interesting thing that needs to be better understood. So if you notice from this animation, we have really high oil pressure in the middle of that bearing, in the middle of its length. That's shown by the Z direction. That high pressure happens at the middle of that bearing's length, but we actually, if you notice, we decrease pressure really rapidly down to 0, or atmospheric pressure, at the edges of the bearing. So that's where your oil is leaking out from the edge of the bearing back into whatever reservoir is collecting it. Now, it's just important to note that that occurs. However, we're measuring bulk strain of the bearing housing, so even though we have less pressure at the edges, the bearing housing is still going to deform due to that transmitted load. But it's just an interesting fact about fluid film bearings that you lose pressure that rapidly across its width. So now that we've talked about our plain cylindrical journal bearing and fixed geometry bearings, I wanted to talk about tilt pad bearings. Now there's a few different styles. There's tilt pad bearings. There's also flex pad bearings. We're not going to talk about them a lot, but a lot of the basic ideas are similar between the two. But there's two main styles of tilt pad bearings that we need to talk about, and that's load over pad, which is showing in the picture on the left, and load between pad, which is shown in the picture on the right. So you can see in the picture on the left that gray semicircular pad is right below the shaft. In the picture on the right, there's two gray semicircular pads that are at an angle relative to that vertical. So these tilt pad bearings of any style, they come in all different numbers of pads. They come in different orientations, different offsets between pads. There's a lot of controls that it can be managed in those. But the big important thing is that the tilt pad bearings use pads with a small angular displacement to support the load of the rotor. The pad rotation provides a reaction force in line with the shaft center, which eliminates cross-coupling. Remember, we talked about cross-coupling a few slides ago? What this means is that tilt pads no longer have an attitude angle that you would see in our fixed geometry bearings. Remember, the line between the shaft center and the bearing center caused if you drew a line between those, you actually had an angle between that line and the vertical. You no longer have that in a tilt pad bearing. The shaft will lift directly straight up in this situation. The benefit of that is tilt pad bearings offer a higher stability than a fixed geometry bearing. So now on this slide we have our pressure distributions for the same startup event for a 5-pad load over pad shown on the left hand side versus a 5-pad load between pad bearing shown on the right hand side. And I want to just talk about the distinction on where we would place our FDS sensors to monitor each of these. For our load over pad, you'll notice that the high pressure oil film region actually occurs on that bottom pad. That bottom pad supports the majority of the load. And so we should be placing our FDS sensor at the bottom dead center position below that lower pad, right? Pointing that sensor towards the shaft. If we look at the load between pad bearing, the two bottom pads, the lower left and the lower right pad, support that load almost evenly, and you end up getting high pressure in your oil film at each of those pads. So if we were to place FDS sensors on that bearing to monitor them, we would want to place the sensors below each of those pads, again pointing towards the shaft. But you would require 2 sensors for a load between pad bearing and only 1 for a load over pad bearing. Thank you everyone for watching this video. This is the last in our introductory series on our Voyager FDS sensor. The next series of videos is going to talk about installing the sensor. We're going to go through examples and video examples of me installing some sensors. So please stay tuned for those. If you haven't watched any of our previous videos, please feel free to check them out on our website at voyagerdynamics.com. Thanks so much. Bye.